All right. See, I don't know what the difference is.
Progress.
Can you hear and see me?
Yes, I can hear and see you.
Perfect.
Yes.
Perfect. All right, now today, we're gonna start so that and I will not go over like I did yesterday or like I did Tuesday. First, are there any questions or concerns?
Yeah, I do have a question.
Go.
So when you record our Zoom sessions, do you post them on something?
I need to post them and I need to figure out how to post them. I will figure it out this weekend.
I know you can do it on YouTube, like that's what my one professor did.
I know I can. I know, but like Toya learned a minute ago, I have a class right before this.
Right.
And I think there's an issue with me being able to record one session right after another.
Gotcha.
And let me see if I can't work through how to do it.
Okay.
Outside of that, are there other issues, concerns? I got a question yesterday in an email asking me about when was it okay to take the chapter quizzes? Let me put it this way. You can take it at any time. you have 2 attempts to take it. Anytime that it's open before it's due, you can take it. I would suggest that you take it after, take it after we finish lecturing about it. At least take 1 attempt after we finish lecturing about it. Because you may learn more than trying to take it without lecture about it. But you can take it whenever you want to. Are there any questions about the quizzes?
How many questions is it, and how much time do we get?
That the first chapter one, I gave you, I think, 42 minutes. I'm realizing that that probably isn't enough time, and I couldn't change it because people had already started taking it. I want to see how you do. But with all of the other ones, it's approximately 22 questions. And you will have 55 minutes to take it. Each one of them will be approximately 22 questions. And you will have approximately 55 minutes to take them. Does that make sense?
Yeah, it does. And like the practice quiz, it's multiple choice mostly.
Well, the chapter quizzes are also, a lot of that is multiple choice too.
Okay.
Okay. So we talked a little bit at the very end about trace elements. These are metals that are vital to the structure of proteins. And remember how structure is related to function. And so trace elements help with catalysts, being able to allow reactions to occur faster and maintain the structures of molecules that are necessary for body function. All elements, bear with me here. All elements are made of atoms. Atoms are composed of protons, neutrons, and electrons. Protons and neutrons reside in the nucleus of the atom.
I'm sorry, are we in chapter 2?
Yes. Oh, you know what? We aren't this far along. If I remember right, are we?
No, we just ended.
We just barely
just-
started chapter 2. I'm so sorry.
We just ended the gradients of
Yeah.
chapter 1.
And
And
so
then-
that is the end of chapter 1. So we're starting chapter 2 today.
And then if you're trying to share a screen, we can't see
You
anything.
can't see it. Oh, well, okay, let me fix that. Give me 1 second here. I apologize. Let me make it so you can see the screen. Now you see it, right? Okay. So chapter 2, the chemistry of life. So this chapter, and you'll see this PowerPoint is 153 slides. This is probably one of it is the longest one that we will have. And probably the most involved chapter when it comes to wrapping your head around it and comprehending. However, life is chemistry, biology. The reason that biology and anatomy and physiology function the way they do is because of the fact that all living things and all non-living things are composed of atoms and chemical elements. And so we have to learn about atoms and chemical elements and how they interact and how they react with one another to understand why biology and physiology and anatomy function the way they do. When you think about it, your whole body is an organization of chemical atoms. And atoms, we'll talk about it here in a minute, but atoms interact in such a way based on their structure. So we've talked a lot about how structure relates to function. An atom structure determines how it's going to function. So with that in mind, this over. Why is chemistry important? Because anatomy and physiology finds its basis in chemistry, and biochemistry being the chemistry that makes up all living things. You remember we talked about this hierarchy of complexity.
Mhm.
Chemicals form macromolecules. Macromolecules form organelles and cells. Cells form tissues. Tissues form organs. Organs form organ systems. So the very basis of all this is atoms. Chemistry is a science of structure and the interactions of matter. Matter is anything that occupies space and has a mass. Different states of matter are solids, liquids, and gas. A mass is anything that has, a mass is any amount of matter that contains a weight. And weight is defined as the force of gravity that acts on that mass. So let me re-go over this, re-summarize this. Chemistry, the science of structure and interactions of matter. Matter is anything that occupies space and has a mass. Mass is defined as the amount of matter a substance contains. Weight is the force of gravity that acts on the mass of the matter. Any questions about that?
Is the definition of mass the amount of matter a substance contains? That's all.
Say it one more time, Toyin.
The definition of mass, is it the amount of matter a substance contains? That's all?
Yeah,
Okay.
so it's essentially the volume of it. And what gives mass weight is the force of gravity that acts on that mass. So if you think when you move away from the Earth's surface, like astronauts do, their weight goes down. Even though their mass doesn't change, their body mass doesn't change, their weight goes down because the force of gravity goes down. Chemical elements are unique substances that cannot be broken down into simpler substances by normal chemical methods. We can't heat them and break them down. We can't blend them up and break them down. We can't cut them up with like a scalpel blade and break them down further. We can't put them in a blender and break them down a little further. So chemical elements are substances that cannot be broken down into other substances by using normal chemical methods like cutting, heating, blending, reacting them with other things and changing them. We can't do that. So a chemical element is a pure substance, cannot be broken down, consisting of only one type of atom. There are 91 naturally occurring elements on the earth. 24 of these are listed here, and they play normal physiological roles in the human body. Several of the elements that make up the human body, being shown here, are minerals that have to be taken in via our diet. They make up approximately 4% of the human body weight. %, so 3% of this human body weight is calcium and phosphate. %1 is chlorine, magnesium, potassium, sodium, and sulfur. For example, and even though 4% may not seem like a big amount, these are vital for your existence and vital for your overall health and well-being. For example, crystallized calcium, phosphate, magnesium, fluorine, and sulfur ions are found in bones and teeth. Proteins commonly contain sulfur. Phosphate is a major component of nucleic acids, adenosine triphosphate, which is our energy fuel of the body, and cell membranes. Enzymes and other organic molecules require minerals to function. Some trace elements are required to prevent disease. For example, an ion deficiency in the, let me back up just for a second here. Our trace elements, these, oh, I get a lot of little pop-ups and I hate them. This right here, this bottom area that is 0.7% of your body weight are our trace elements. Trace elements prevent, or even though it's only 0.7% of your body weight, they're required to prevent disease. For example, an iodine deficiency prevents the production of thyroid hormones, resulting oftentimes in what's called a goiter. If you look at this lady's neck right here, you see that enlargement on her neck. What that means is that her thyroid gland, where her thyroid hormones are produced, has become enlarged because it is trying to make up for the fact that the normal size of the organ is not producing enough thyroid hormones. So to compensate for that, it's become bigger and become a larger organ. Question for you, why don't we see a lot of thyroid goiters here in the US?
Because we have iodized salt.
Oh, you are smart. Where did you learn that, Claire? She's got it. She's thinking to herself, where did she learn that? You're on mute a little bit too.
Oh, my grandfather had a goiter, and I knew that from because of there's iodine in the salt. And then I think iodine's supposed to help with radiation in the atmosphere too, to protect your thyroid. I'm not sure.
Maybe. I don't know that,
Be
but
wrong.
yes, possibly. I didn't know that. But yes, that's 100% correct. That's the reason that when you buy typical salt in the store, such as Mortar's salt, it's all iodized. And so rather than have it be sodium chloride, which is normal table salt, it's sodium iodide, like Claire said. So the thyroid enlarges to try to make up for the fact that you have an iodine deficiency. Also, without iron, your body cannot transport oxygen. If you've ever heard of someone becoming iron anemic or becoming having anemia, as let's see, older teenager, I was about 18, I was diagnosed with being iron anemic. I had a lot of surgeries growing up, and one of the blood test results they got right before I had surgery, it showed that I was anemic, meaning my red blood cell count was down.
I currently have anemia. I don't know if you noticed I was laying down last week.
Nope, I didn't. But you were
Probably
laying
why.
down. What
Yeah,
are
but
you doing? What are you
I'm
doing?
taking ferrous sulfate. I just had some minor surgery done, and I have post-operative anemia. And I swear to God, a week ago, without the iron, I swore I'd never leave my bed again. But then since I I like literally was lightheaded and dizzy. I wasn't getting enough oxygen to my head. Like
Yeah.
there wasn't enough oxygen going around my body and made me very sick.
Mom, come here, mom, listen to what she said. Claire, tell your story to my mother, who's my lab assistant, my teaching assistant here, who is a retired nurse practitioner.
Yeah, I have post-operative anemia.
Uh-huh.
And 5 days ago, I would have sworn I was never going to leave my bed for the rest of my life. And my doctor's like, you need to get ferrous sulfate. It's a recommendation over the pharmacy. And 5 days into it, I'm back at work and I'm fine. But I was lightheaded and I felt like I was never going to leave my bed, like ever. I was like, I don't know what's wrong with me. I'm so sick. So here
Yeah,
I am. I'm feeling
Wow.
great, really.
giving your
Wow.
body the building blocks to replace the red blood cells so
Yeah.
that you can
It's amazing.
create
Absolutely.
the oxygen carrying capacity. And
Yes,
are you staying well hydrated?
I am. I was
Good.
also advised to do that.
Okay, great.
When next semester, at the very beginning of the semester, one of the very first things you talk about is blood flow. And you'll learn why that hydration was so important and why you were feeling lightheaded. But good, that very good example there. Ferrous is, it means iron. It's one of the ways that we describe an iron supplement or an iron molecule.
Ferrous sulfate is the form most easily assimilated by the body.
Did you hear that? Say it, Mom, you gotta say it so we can hear you.
You can't repeat it.
I can't say it as well as you do.
I said ferrous sulfate is the form of iron that is most easily assimilated by the body. And that's why it was recommended for you.
Thank you, Mom. Okay, so fluoride is usually added to municipal water and dental products to help reduce tooth decay. So atoms are the building blocks of elements. Atoms are composed of protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. The electrons are found surrounding the atom. When we tend to diagram atoms, we draw them as being found in electron orbits. Tend to find them in electron orbits. That's the way we draw it. We call this the Bohr or the planetary model, meaning that the electrons are orbiting the nucleus. However, we know this is only the way that we draw this. This isn't the way that in actuality they are found. The way that it's actually found is that the electrons are in a cloud orbiting around the nucleus. Electrons are really, 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 really small. And at any given time, we cannot pinpoint where one particular atom is. However, on average, we can say that they're probably in that one of the orbits. Most likely that's where they are. That's why we use a Bohr model, but we know that this is more like what it actually looks like. So when we talk a lot about atoms, we're going to use the Bohr model idea. but recognize that at any given time, they may be in between the orbits. But on average, they're in certain areas, certain higher concentrations within the cloud, which we call the orbits. Is that clear? So electrons forming the electron cloud in an atom occupy regions of space called the electron shells or orbits. And each shell contains one or more orbits. The smallest particles of an element that can still exhibit the chemical properties of that particular element is the atom. If we remove electrons or protons or neutrons from that atom, it will no longer exhibit the chemical properties of the element it was before. So if you think, remember, keep in mind all the time, the structure is related to function. If we change the structure of something, we change the function of something. So if we remove a proton or neutron or an electron from an atom, we're going to change the function of that atom. It's no longer going to function the way it should have, the way it did before. So some typical Bohr models of atoms. Hydrogen has one proton and one electron. Protons are positively charged. Neutrons are neutral, and electrons have a negative charge. So if a proton has a positive charge and an electron has a negative charge, what do you think keeps the electron orbiting around the nucleus? When you think about charges,
The negative charge?
the negative charge and the what, Brittany?
The negative charge within the would it be within the nucleus?
When what's within the nucleus? What
Maybe I'm
else? You're on the right track. I'm leading you a certain way. So the electron with its negative charge and the positive charge of the protons.
okay.
You were exactly right. So the electrons, the negative charge of the electrons is attracted to the positive charge of the protons,
Yes.
which is what keeps the electrons orbiting around the nucleus, like Brittany said. This first shell can contain up to 2 electrons. If an atom has more than 2 electrons, all other shells can contain up to 8 electrons. The most outer shell of an atom is called the valence shell. Example, we have nitrogen here. Nitrogen has 7 electrons. It has 7 protons. So 1 negative charge, 1 positive charge. Has a balancing effect here. Or the positive charge on the proton neutralizes the negative charge on the electron to give the overall atom here a 0 charge. So 2 electrons here in the first shell of carbon, 4 in the second shell, which is its valence shell. So carbon has 6 electrons, 4 in its valence shell, its most outer shell, and 2 in its first shell. Nitrogen has 7 electrons. It has 7 protons too. This number that we'll talk about here in a minute, atomic number, is the sum of the number of electrons and the number of protons. But with regards to the electrons here, 2 electrons in the first shell, because nitrogen has 7 electrons, 2 in the first shell, 5 in the next, because altogether the nitrogen atoms have 7 electrons. Oxygen, 2 in the first shell, and because oxygen has 8 electrons, there's 6 in the next shell. Phosphate has 15 electrons. First shell contains 2 electrons. Second shell contains 8. Third shell contains 5. If the atom fills up this shell, like sulfur, or it's going to keep filling up that third shell until it reaches 8 electrons in that shell. And then it will have another shell to give it more, allow it to have more electrons. So 2, 8, 8, 8, 8 until we fill up all the shells, so we've used all the electrons we have for an atom. Is
Okay.
that, go ahead.
How comes the atomic number is 31 when all the other ones, the atomic number is the bottom number multiplied by 2?
That's a really good question. And I think, if I'm right, it has to do with the fact that there's an isotope involved here.
Okay,
Bear with me there, all right?
all right.
Because that's a really good question. And I think it's because we're referring to an isotope here, which we'll talk about soon. So valence is the most outermost shell. Elements with their atoms are arranged on a periodic table according to their atomic structures, the structure of the atom, which results in the structure of the atom. If you think structure, function, the structure of the atom dictates the different functions / properties of an element. I think I meant to use a different PowerPoint here. And I didn't do it. I'm gonna skip around here and I will fix this in a little bit. But I'm gonna skip over that slide just for a moment and come to this one. So knowing that the elements are described according to their chemical structure, atomic structures. On a periodic table, all of the elements of one horizontal row, which is referred to as a period, have the same number of electron shells. So helium, see, hydrogen has one shell. It has one electron. Helium has two electrons. We know that we can put two electrons in the first shell. So both helium and hydrogen have the same number of electron shells. With on the second period or the second row, have each of the atoms of these elements have two electron shells. Third one, each of these have three electron shells. So the periods of the horizontal rows across the periodic table are arranged so that all of the elements in that row have the same number of electron shells. Each group, so this is vertical rows, vertical columns. The elements of each group have similar chemical properties. They react with they react with the same atoms in a similar fashion. So they react with the same element, other chemical elements similarly. So groups, periods are arranged where the one period, meaning one horizontal row, has the same number of electron shells. Groups are the vertical row columns where the elements all in this column, their atoms have the same chemical properties. They react the same way with other atoms. Okay, now I've rearranged this a little differently, and then I didn't do it, and then I posted it wrong. I'm gonna back up just a little bit here. Oh, seriously. There. Bear with me. So the atomic number of a chemical element is the number of protons within an atom of that element. So the atomic number is the number of protons within an atom of a given chemical element. So for example, hydrogen has 1 proton. Therefore, its atomic number is 1. It's often seen up here in the upper left-hand corner. The number of electrons will determine, though, the chemical behavior of that atom. And for an atom with a 0 charge, a neutral charge, the number of protons is going to equal the number of electrons. Because remember, protons are positive, electrons are negative. So when the numbers of protons and the number of electrons equal one another, the overall charge on this atom is 0. The mass number is the sum of the number of protons and neutrons. Neutrons have a very, 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 very small weight. Many times, oh wait, let me not say that. I'm not going to say that, never mind. Isotopes are atoms that have the same number of protons and the same number of electrons, but the number of protons may not equal the number of neutrons. So isotopes are atoms with the same number of electrons and protons. So they have a 0 charge, but normally when the neutrons should equal the number of protons. And in an isotope, that isn't the case. So isotopes are atoms with the same number of protons and the same number of electrons, but they contain different numbers of neutrons. So the mass number is the sum of the number of protons and neutrons. The atomic weight for any given chemical element is the average weight of the mass numbers of all of the isotopes of an element. So in this case, this is the atomic weight of hydrogen. Remember that neutrons carry very, very, very little weight. And so they carry a little bit, but not very much. There are 3 different isotopes of hydrogen. If you saw the hydrogen atom by itself right here, does not have any neutrons. However, deuterium has 1. Tritium has 2. These are both isotopes of the hydrogen atom. So these are hydrogen atoms, hydrogen elements that have neutrons present. 11 inches. So with this in mind, if the element lithium has 3 protons and 4 neutrons in its nucleus, what is its mass number?
7.
Correct. Good job. An atom with a mass number of 18 that contains 10 neutrons would have an atomic number of what?
8.
Correct. Because remember, the atomic number is just the number of protons. Let me ask you another question with regards to this one. How many electrons does this have? This atom. It has a 0 charge on it. It's a stable atom. How many electrons does it probably have?
Does it have 8?
How did you know that?
Because protons and electrons are the same.
Right, correct. Let me ask you another question. How many electron shells does it have?
Would it just have 2?
Why?
Because the first shell would have just 2 electrons and then the rest would be on the second shell.
And how many are in the second shell? I'd say about 6. You're right. Is that clear?
Yeah, so the shells is the sum of the electrons. Or
The shells are where all the electrons are going to be.
Okay.
And you put 2 in the first shell, and all of the other shells can hold up to 8. And we'll talk about the significance of that in a little while here.
So you said was it electrons and protons are the same?
Protons are positive charged. Protons are, I'm sorry, say it one more time.
That because the answer was 8, the protons and electrons are the same.
They equal. Yes, their number equals.
Okay.
Most oftentimes, if the atom has a charge on it, they're not going to equal, but we'll talk about that here in a little while, okay? So isotopes have the same number of protons, same number of electrons, but different numbers of neutrons. In a normal everyday atom, the number of neutrons will equal the number of protons. However, when that's not the case, let me put this another way. The number of neutrons will equal the number of electrons in an everyday normal atom. That's not really, you know what, I'm making this way too complicated. Isotopes have the same number of protons, the same number of electrons, but different numbers of neutrons. All of these are hydrogen, deuterium, and tritium are all isotopes of hydrogen.
I'm sorry, could you repeat what you said about the isotopes?
Which part?
You said that they're the same number of electrons and same number of,
They have the same number of protons. They have the same, all atoms, chemical elements all have the same number of protons and the same number of electrons. So all atoms of one chemical element have the same number of protons, the same number of electrons. However, isotopes of that atom are going to have different numbers of neutrons. Is that clear? So all hydrogen, deuterium, and tritium are all atoms of hydrogen. However, each of these have a different number of neutrons. This has no neutrons. This has one. This has two. So they're all atoms of hydrogen. But they're isotopes because each one of them has a different number of neutrons. Is that clear? Kind of, maybe? Let me move forward. So recognize in all atoms are going to have the same number of protons, the same number of electrons. Isotopes of that atom, however, can differ in the number of neutrons. Isotopes are unstable atoms that can lose nuclear particles until they become stable. Heavier isotopes of some elements are very unstable, and their atoms can decompose spontaneously into more stable atoms. There are many isotopes, but heavier isotopes tend to be unstable, and they will decompose until they become more stable. These unstable isotopes are called what? Radioisotopes. The decomposition or atomic decay is called radioactivity. This decay involves the emission of alpha, beta, and gamma rays from an atomic nucleus. These elements can transform into other elements. When an isotope gives off an alpha emission rays, it gives off helium nuclei until it becomes stable. This is what we call alpha emission. Other isotopes will give off electrons in the form of beta emission rays. Other isotopes will give off photons, light rays, which we call gamma emission rays. They will keep decaying until they become more stable atoms. Please stop me if you need me to.
What happens if they don't transform into other elements?
Then they stay fairly stable.
Okay.
And sometimes it takes a very, 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 very long time. So radioisotopes gradually lose their, sorry about that. They gradually lose their radioactive behavior. So the time required for a radioisotope to lose its 1/2 of its activity and become a more stable atom is its physical half-life. So 1/2. So if you've ever heard of medicines having a half-life, a half-life meaning the amount of time you ingest a medicine, and the half-life is how much time passes before only half of that remains in your body. Kind of like Claire with the ferrous sulfate. She takes a ferrous sulfate pill. The half-life is how much time remains before whatever her body hasn't used is eliminated from her body. So the half-life is how much time is required for a radioisotope to lose half of its activity and become a more stable atom. Half-lives can vary between hours to thousands of years. Like I think Brianna asked about what happens if they don't decay. Well, they may not be very unstable. So they may just remain for a long period of time, and some half-lives can be thousands of years. So the biological half-life, just like a medicine, is how long a radioisotope will, how long will it be until a radioisotope loses half of its radioactivity within the body? So how long will a radioisotope, how long will it be before a radioisotope loses half of its radioactivity within the body? I'm gonna add a word in here later, half of the radioactivity. So radioisotopes, as we learned, we were talking about last week, we were talking about positron emission tomography, where we introduce a radioactively labeled tracer metabolite, usually oftentimes glucose. And we watch their emission. We watch how much radioactive decay comes off. So radioisotopes can be used for biological research and medicine because they share the same chemistry as more stable isotopes. We can use them to localize and illuminate damaged or cancerous tissues. This example right here, this is Graves' disease or hyperthyroidism. A normal thyroid would put out if you introduced a trace amount of radioactivity, would emit a little bit. In Graves' disease, where the thyroid becomes really big, it's going to emit a lot more. So remember, so we talked about positron emission tomography, where we use radioactively labeled substances to measure the metabolic activity of different things. Cute dog. In this case, so just to expand on that positron emission tomography, we use radioisotopes in that, and that we measure the amount of decay that they're putting off through their metabolism. So we talked about positron emission tomography. Now we're talking about how what we use in that is actually radioisotopes. So alpha emission is the least penetrating, meaning the least damaging of radioactivity. However, inhaled alpha emission particles from things like radon, which is caused by the decay of uranium, causes lung cancer second only to smoking causing lung cancer. Gamma emission, remember these were photons, has the greatest penetrating power used to destroy localized cancers. Ionizing radiation, which we'll talk about specifically why we call this ionizing next time. Ionizing radiation knocks electrons out of atoms, and these electrons then go on to destroy other things. And we'll talk about how that works next time. Our class goes until 1:45, right? Or is it 1:40?
1:45.
Okay. Okay. So different alpha emission, least penetrating, least damaging. Gamma emission, greatest penetrating power, used to destroy local cancers. Ionizing radiation off radioisotopes knocks the electrons out of atoms, and these electrons then go on to destroy other things. When I say destroying other things, remember we talked about electrons, how they dictate the function and structure of, they dictate the behavior of atoms. So if an electron here, if this atom right here loses an electron, this electron can then go and bind with another atom and change this function of that atom. And when we start changing the functions of things randomly, we start causing chaos. So that's how they destroy other things. For any particular element, the number of blank can vary, and therefore the mass number of the element will vary. What do you think? What would cause variations in the mass number?
Neutrons?
The neutrons, correct, Kevin.
Neutron, yes.
Yep, Toyin, correct. Inorganic compound salts. Ionic compounds contain cations other than hydrogen and anions other than hydroxide. Cations are positively charged atoms. Cations are positively charged atoms. What this means is that we've lost an electron and the number of protons now exceeds the number of electrons. So the overall atom has a positive charge. The number and anions are negatively charged. So that the number of, we've gained an electron and the number of electrons is now more than the number of protons. So the overall atom has a negative charge. When these ions dissolve in water, they dissociate. Ions are electrolytes. Things with a charge can conduct an electrical current in a solution. So we call them electrolytes. The most common salts found in the body are sodium chloride, calcium carbonate, and potassium chloride. Other common ions are iron, copper, zinc, iodine, and magnesium. So wait, I'm going to go back up just a second here. So an anion is a neutral atom that gains an electron, giving the atom an overall negative charge. A cation is a neutral atom that loses the electrons, resulting in a net positive charge of the atom. Ions that have opposite charges can become attracted to one another. Remember, if you think positive charge, negative charge, they attract one another. We're done here. Are there any questions? I will see you on next Tuesday.
Thank you.
Thank you. Bye-bye.
Thank you. Have a good day.
You too.
Thank you.
You too. Linnea?